Alrighty, Math 10. So in this video, we're gonna start on our new chapter, which is relations and functions. So we're gonna start with 5.1, and that's essentially just talking about and analyzing functions in a bunch of different ways, and relations, sorry, mainly relations. You gotta understand that in the realm of math and just any day in the world, there are relations all around us, okay? The amount of, let's say, bunnies is related to where you're located and the climate. There's a relation between the amount of money you make depending on the job you do, okay? So what a relation is and what we do in math with relations is we analyze these in a mathematical way, okay? And we're going to do that pretty much in the next few videos here. So let's see what we can do after this video. So after we hopefully can do all of these, so explain the relationship between data, okay? So that's essentially determining and explaining the relationship between a relation. We need to be able to show a relation in multiple ways. So this video will talk about using a table, an arrow diagram, and ordered pairs, okay? Ordered pairs is where you set up and you say like 4 and 5, 2 and 3. This would be one ordered pair, and this would be another ordered pair, okay? You also want to convert between graphs, tables, ordered pairs, and diagrams. So you can relate and show relations in multiple different ways. And then we want to understand the difference between continuous and discrete data. This is something you might have touched on a bit in grade 9, or you might have just seen in your regular day life, but we're going to actually mathematically now determine that. So let's move forward and let's talk about what a relation is. So relation is an association between two quantities that can be represented in a variety of different ways. These ways can be words, a graph, an equation, a table of values, or ordered pairs. Sometimes relations linear or nonlinear. The word linear means straight. Okay, the word nonlinear just essentially means that the relationship is not straight. Okay, it could look like anything as long as it's not straight. It's not a linear relation. Okay, and in grade 10, you learn how to make graphs for linear relations. So we can kind of see here, everything here is listed below, and this is just one really quick example. So this would be a linear relation, and again, aka it means it is a straight line. You can see here that we have a relation in words. 3 times the length of your ear is equal to the length of your face, which is kind of weird, right? So essentially your face is 3 ear lengths long. And we can see that is a straight line. If we plotted this, let's say you have 2 centimeters for ear length, you can see here that that's going to actually equal up to 6 centimeters for your face length, okay? Because it's 3 times your ear length. We can see here that 4 times your ear length, well, that relates to how much? Well, 4 times 3 is 12, so this would be 12 centimeters here, okay? You can see on our nonlinear side, okay, so not a straight line, the area of a circle is equal to pi times the square of the radius. So this is something you're not really going to deal with in grade 10. This is stuff that more you think about in 20-1 and 30-1. But you can see we don't have a straight line. This thing is increasingly growing faster and faster and faster. Okay, just so you're aware, this is known as an exponential growth. We can show both of these relationships in terms of an equation. And here we want to put F as face length and E as ear length. So anytime you create an equation, you need to make sure you state what type of variables these represent. So what does F represent here? Well, F represents the face length and E represents your ear length. Over here, R is your radius there, okay? This equation is actually not true. It should say area equals pi r squared. I must have missed putting the pi in there. That's okay. Okay, where R is your radius and A is your area, and in this case of a circle. Okay, so you can see that we've not only been able to relate things in words, we used a graph to show, and this equation is actually related to this graph. This equation is related to this graph. Now we can put a table of values. So as we can see here, we have our ear lengths on the side, on our left-hand side, and our face length on the right-hand side. And we can see that these are increasing by the same amounts. That is why it's a linear relation. So we can see 6 plus 6 equals 12, 12 plus 6 equals 18, 18 plus 6 equals 24. We can see on this side, it's also going up by the same continuous growth. So this would be plus 2, 4 plus 2 is 6, 6 plus 2 is 8. So we'll talk about more of this later, but we can see, based on the table of values, that this is a linear relation because things are going up by the same amount. Over here, not quite. You are not going up by the same amount at all. You can see these numbers are continuously changing, okay? To get from 25 to 100, you need to add, in this case, you need to add 75 pi. To get from here to here, you need to add even more. This would be 125 pi. So you can see we're not increasing. As soon as one side is not increasing by the same amount, you are no longer dealing with a linear relation. And here's our ordered pairs. So we'll talk about how to set these up. But in order to set up ordered pairs, you need to use these little squigglies, and everything inside is an ordered pair. Okay, so here, these are two ordered pair. So when you have an ear length of 2, you have a face length of 6 centimeters. Ear length of 4, you have a face length of 12 centimeters, so on and so forth. Okay, so let's get to some definitions here. So we need to know the words set and element. So a set is a collection of distinct objects, okay? So up here, we have a set of ordered pairs. On this side, we also have a set of ordered pairs. In order to show a set, we need to do squigglies inside, or on the outsides, and then we list all these things a part of the set. Okay, so this whole thing is known as a set. And then your elements are the single objects inside your set. So each individual thing would be a element. So the sentence can help us understand what this means. A set is a collection of elements, okay? So you could have a set of video games, okay? And each video game would be an element. Each game equals element. Okay, so here we can see a quick example. We have our squiggly brackets here, and now inside these squiggly brackets is a set of something. In this case, it's the elements are the individual numbers. Okay, if you ever see a 3 dots at the end, this means it just keeps going on and forever and ever and ever. And usually there is some sort of pattern that you might see, depending on what type of relation you're talking about. So let's see an example here. So example 1, school grades can be associated with the division they fall into. Consider the relation represented by the table below. So we can see we have grades and we have a division that it's a part of. Okay, so a grade 2 is a part of division 1. Grade 5 is part of division 2. Grade 8 is part of division 3. We can describe the relation in words. Okay, how do we describe this relation in words? Usually, if they tell you up here, it's almost listed in types of questions. But to actually describe this relation in words, we would describe it as grades it would be grades fall into specific division. Okay, we could also explain, if we put a title above here, so every single table should have a title. So if we wanted to represent this title, we would read it as grade 2 is a part of division blank, or division 2, okay? So if we were to put a title above, you might not have enough room, but this would say is a part of. So now we can read it as grade 5 is a part of division 2, right there. Okay, so let's represent the location, so these guys, as a set of ordered pairs. Okay, so let's go with I here. So ordered pairs remember, is each individual element, okay, in our left-hand column is related to a right-hand column. So number 2, grade 2, is related to division 1. So that is an ordered pair. So this is an ordered pair. This is an ordered pair. Ordered pair. That's how a table of values is set up. So to put this set, we would put a squiggly. And now I'm going to put 2 and 1. Okay, so I get 2 and 1 here. So 2 and 1. My next set of ordered pairs would be 5 and 2. So I'm going to put a comma. And now my next ordered pair would be 5 and 2. Comma. And now I'm going to do 8 and 3. Okay, comma. And this is going to keep continuing. So 3 and 1, comma, 1 and 1. And then I have grades 12 and 4. So 12 and 4 here. 10 and 4. And 9 and 3. And lastly, 7 and 3. And then I'm going to end off with a squiggly. Okay, a squiggly bracket. Now, all of these are related, and each element is actually made up of an ordered pair. So my elements here, my elements are ordered pairs. Okay, and each ordered pair shows me the grade at which I'm talking about. So like in this instance, grade 2, and the division it falls into. So 1. So it's useful to represent things in ordered pairs. Let's use an arrow diagram. So what does an arrow diagram need? An arrow diagram needs a title that explains a relation. Just like every single table should have a title that explains the relation. So here, it's going to look very similar to my table, except now I'm going to use an arrow diagram. So I'm going to put a circle here that represents everything that is a part of my grades. So this will be my grades. Then I'll put another oval here, and make sure you give yourself enough room here, and this will be my division. And then what's my title going to be? So my title will be grades blank is a part of division blank. So now let's write out all of our elements here inside my grades. So the elements would be 2, 5, 8, 3, 1, 12, 10, 9, and 7. And then in my division over here, well, that will be 1. And here, I'm going to actually do something that's going to save me some time. Recognize I only have 4 divisions popping up here. So here I'm going to just put 1, 2, 3, 4. Because what an arrow diagram does is I can actually represent these in a little bit of an easier fashion, okay? Because some of my elements in my grade set are related to the same elements in my division set. So here, grades 2 is in 1. So this will be over at 1. Okay, and you can see my arrow there. Where's grade 5? Grade 5 is in 2. So that will go to 2 here. Grades 8 is in 3. Okay. Grade 3 is in 1. So now we have our first element in my grade set that goes to a division that's already been used. Okay. Grades 1 is also in division 1. So we're going to have another line that points to grade 1. Grades 12 is in 4. So that's our first 4th division grade. Grades 10 is also in division 4. Grade 9 is in division 3. And lastly, grade 7 is also in division 3. So maybe I'll use one more looking color there. Well, let's use black, and then we can see here. So the nice part about doing it this way is I can actually see, hey, I only have one element from my grades that I have listed in grade 2. And we can see that's 5 there. Okay, and this can actually help us figure out maybe what grades would be missing. So here, grades 4, it looks like I'm missing grade 11 in between 10 and 12. So if I had grade 11, I could essentially deduct that grade 11 is a part of division 4. I could also figure out that this goes 1, 2, 3, and then 5 is in division 2. So division 4 could either fall in division 1 or 2, but that's a little above our pay grade right now. But you do need to know how to set up a arrow diagram from a table of values and how a table of values relates to ordered pairs, okay? And being really concise and organized can help you in this by far, definitely. Now, recognize we need our titles, okay? So we put is a part of, so now I can read it as grades. Grade 8 is a part of, and it goes to division 3. Okay, so the titles are really important. Okay, so the last thing I want to hit on is, actually not the last thing, we have a few more to go here, and that's okay. Let's talk about discrete and continuous data. Okay, so this is something you may have already talked about in previous grades or come across in just your everyday life. But what is the difference between discrete and continuous data? So discrete is data that can only be expressed as certain values. So usually we deal with just integers. So like 1, 2, 3, 4, so on and so forth. The important thing to understand is on a line graph, they cannot be connected because what we're talking about doesn't exist in between the 2 points. So here we can see a graph that says number of days passed and number of text messages received. So here, like on the first day, we received none. Okay, we don't have a point. But on the second day, we received 4. Now, we wouldn't connect, so you don't have to write this, but we wouldn't connect these points, okay? Because can we have half a text message be received? No, we can't have 1.5 text messages received. So we can't really see a trend here because we cannot connect these points because this is known as discrete data. Okay, text messages only come in 1, 2, 3, 4, 5. Okay, so when you have discrete data, it's actually better to represent discrete data probably as a bar graph. Okay, or this is also known as a histogram. So here we can read it a little bit better. So we have a title. So every single graph needs a title. Amount of text received after a certain number of days. Because now we can see, hey, on the number of days passed since Sunday, so on Monday, we didn't receive anything, but on Tuesday, okay, you can see that we received 4, okay? This is on the 3rd day after Sunday, so that would be Wednesday, we received 3 text messages. Okay, so you can see how this is way easier to read than this. Okay, so again, discrete data, you cannot connect. Continuous is a little different. It's data that can be any number. Okay, so on a graph, on a line graph, these points can be connected. Okay, they can be connected because the points in between our data values can exist. So here, let's see here. We have average temperature. So temperature, you can technically have temperature that maybe ranges like 4.5 degrees Celsius or 7.1 degrees Celsius. You could technically have a 7.001 degrees Celsius. So in that fact, and if you think about it, we don't just go from minus 20 to this is roughly negative or minus 2. Okay, we're going to have to warm up slowly. Then we're going to have to decrease to get down to minus 10 again. And in order to get from minus 10 to 5 degrees Celsius, well, we're going to have to warm up over the days. Like imagine if we just went from minus 10 and all of a sudden, snap, we're at positive 5. That doesn't make any sense. So we can connect these data points and see a trend. Okay, and it's again because the numbers exist between the plotted points. So that's what continuous data is. It's where things in the middle between your data values exist. Therefore, we can connect our points here. Okay, so that's the big difference. Here's a quick little representation here of what we kind of talked about. So we have data, okay, we have qualitative and we have quantitative. So qualitative is just saying something. It was great fun. But quantitative is numbers, okay? That's what quantitative means, numbers. And with numbers, we can either be discrete, okay, so just individual things that don't really connect to each other, or you can have continuous, so something where you have things that can connect. Okay, so now that we kind of learned what discrete and continuous means, we need to know how to represent data in graphs. Okay, so here we've just talked about describing things with words. We've talked about ordered pairs, arrow diagrams, and tables, but we're missing our graph, which is really important. So here, we're going to learn how you are able to graph specific relations. You're also going to have to know whether the data is continuous or discrete. And that is because if your data is continuous, we can connect, and if it's discrete, we cannot connect your plotted points, okay? And that's what we just talked about. On your graphs, everything, okay? This doesn't only include your graphs, okay? This should include also tables, okay? And arrow diagrams. For some of these, obviously. Not all of them, because on your, you don't have an X and Y axis, but you do have these points here. So with these, you always should have a title. So you can see here we have a title for both of our values. You need labeled X and Y axes. So in this case, for like a table, we need to label what these are. So what do these numbers represent? Well, they represent age, and they also have the units here. So years, this is centimeters. This is the height column, okay? Here, we don't really need units because there's no units for a bicycle or a car, and we understand that these are wheels or tires, okay? But if something is a measurement, you need to have what that measurement's unit is. So let's do this. Draw a graph to represent the following relations. Is the data discrete or continuous? So some things to recall from grade 9 or whatever other courses you've done. When you draw a graph, okay, you need an X and a Y axes, okay? So here, your horizontal is always well, not always, but usually we say our horizontal is our X and our vertical is our Y, okay? Whenever you're dealing with a table, these front columns are usually your X values and these are usually your Y values. Okay, they're gonna be represented with different letters sometimes. That's something really important to understand. We're gonna talk about it later when we talk about dependent and independent variables. But for right now, it's just getting a kind of a taste of what it means to graph something. So here, recognize that we have points plotting. So I'm gonna make this bottom my age. Okay, so this is gonna be the age. This axis here, this is gonna be the age axis, and it's measured in years. My Y, which is gonna be my height, that's gonna be my height axes. So here I'm gonna represent my height. And now when you plot a table, you need to make sure that these numbers go up by the same increments, same as these numbers here, okay? So what does that mean? Well, here I can see that I start at 10. So at the moment, I don't really need, I should start at 0, of course, and go up to 15, but I'm not gonna have any points for those first few, which is okay, sometimes you don't. Okay, so I'm gonna go up by ones here. So this will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, what are we gonna do here? How about let's go up by 2s? Okay, so sometimes, and I'm gonna keep this in because sometimes your scale at the first try doesn't work out, and that is okay. Okay, so it's just a matter of erasing and saying, well, let's just go up by 2s. That'll make it a little easier. So 2, 4, 6, 8, 10. That's a 10, not 110. 10, 12, 14, 16. Okay, good. So we're past our 15 mark here. Now, my height here, I start all the way at 137. So what can I do about that? What I'm going to do is I'm going to erase this bottom portion here, and I'm going to put a little squiggly. Okay, what does a squiggly mean? Squiggly means that we're not starting at 0. Okay, and this is something hopefully you learned in grade 9. So if I put a squiggly there, I just simply don't start at 0 and start counting, because I'm going to start all the way at roughly 137, okay, because I got to get up to 157, which is 20 points. So I'm going to go up by 2s as well here, but start at 130. Okay, so 130, 132, 134, 136, 138, 139, or that would be 140, sorry, going up by 2s there, 140, 142, 144, 146, 148, 150, 152, 154, 156, 157. And you can see I've roughly spaced these points by the same amount, and I've went up by the same increments. This is going up by 2, this is going up by 2. Your x-axis can go up by different increments than your y-axis, okay? But in this case, it just made more sense to go up by the same amount. Remember, I put a squiggly here because I didn't start at 0 here. I started at 130. Now let's plot these points. So at age 10, which is right here, okay, I was 137 centimeters. And technically I wasn't, because this was the height for females, but whatever. So for a height of a female at age 10, she's roughly 137 centimeters. So at age 10 here, we're 137 centimeters. So you got to usually use a ruler and try and line this up here. So 137 falls right in between there, and we will be plotted right about there. Okay, so let's try and plot that pretty accurately. So I'm just going to do some dotted lines to try and accurately represent where this intersects. And my intersection point is found right there. Okay, and you wouldn't keep these dotted lines in, they're just a point of reference to figure out where exactly you should plot your point. Okay, so now we go on to age 11, which is 139. Okay, so pretty close. Now age 11 falls in between 10 and 12. Okay, so I'm going to draw my line. Again, you'd probably use a ruler to help you figure this out. And then 139 roughly lines up right there. Okay, and then I will get rid of these little plotted points so I don't confuse myself. There we go. Okay, and you just keep continuing. So 12 years old, it looks like this girl went through a growth spurt and got to 145 centimeters. So age 12 is found right here. Let's draw our points as straight as we can. And what were we at? 145. So we definitely had a growth spurt, because look at that increase. We pretty much roughly go right about there. Perfect. Okay. And again, you probably don't have an iPad where you can just erase it super cleanly. So I would suggest using a ruler to line these intersection points up. Okay. Age 13 now. Where am I? 152. So 152 at age 13. Age 13 is found right in between 12 and 14. So let's draw our estimated point here. And again, when I'm 13, I'm 152 centimeters. So another growth spurt at that point. So that's pretty crazy. So it looks like for females, when they're between the ages of 11 and 13, they go through a massive growth spurt, okay? And then here now age 14 is found right here, and we're going to be 155 centimeters. So at 14 years old, 155, which is right about there. So we will plot our point there. And now you can see that our growth isn't quite as drastic compared to our other ages, right? So from here to here and here to here, that's a pretty small growth comparatively. And lastly, we're going to go to 15 years old, and that's 157. So 15, we will just miss this point, and we will be at 157. Technically, this should be 158 because our point should have went up by the same amount, and we will meet very closely. So it looks like our growth spurt is done, and we are now kind of plateauing at whatever height this female will be for the rest of her life, until she gets really, really old and then she starts shriveling up a little bit. But that happens to everyone. You start getting shorter as you get older. So now the question is this discrete or is this continuous? Well, let's talk about that. Can I be in between my points that I plotted in both my y and my x-axis? Yes, you can be between the ages of 10 and 11. You can be 10 and a half, you could be 10 and 3/4. And your height, absolutely. You don't just randomly shoot from 145 centimeters right up to 152 centimeters, right? In an instant, that doesn't just happen. So these are continuous data points. So we can connect these and form a trend, okay? And you can see visually that we shoot up. So this is our growth spurt here, and then we start kind of plateauing. So this is continuous data. Okay, because again, all of these exist in between. The points in between exist. And yeah, that's how, what are we missing here? We are missing a title. So we have our units on our x-axis. We have a label. We have a label for our y-axis. We have units. We don't have a title. What the heck is this all about? Who are we talking about, right? Well, we got to put up here, this is the average height of a female. And yeah, average height of a female. And that's enough of a title to explain what this graph is all about. Okay. So there's our table. Let's maybe move on to one more example. And here we're going from a line graph, or sorry, a line diagram to a graph. So it's the same idea. Let's draw our y-axis, aka our vertical, and then let's draw our horizontal axis. Okay. Now looking at this, my question is, should I use a line graph or should I use a bar graph? Well, here, hopefully you can already see that this is definitely going to be discrete data. Here we're just talking about certain types of categories. So a bicycle, a car, a motorcycle, you can't have in-between things here. So as soon as you have one of them that can't be in between, okay, your data isn't continuous in one of your sets, then therefore it is a discrete data. Okay, because you can't have, it makes literally no sense to be in between a bicycle and a car. We're not talking about hybrids here. Okay, so here I'm going to put what's on my left side, okay, my left of my arrow diagram on the horizontal axis, known as the x-axis usually, okay? And I'm going to represent these as simply bicycle. I spelled bicycle wrong already, look at that. So bicycle, then I have a car, I have a motorcycle, I have a tricycle, and then I have a unicycle. Okay, so here I still need to label what this is. So this is type of vehicle / bike. Okay, and these have no units. Over here, I'm going to put what's on the right side, on the right element set. I'm going to represent that on my vertical axis. And this is going to be number of wheels. Okay, and of course I need a title. So this would be number of wheels on certain vehicles. Okay, and then from there we can start plotting. So here I only go up 1, 2, 3, 4. So that's going to be pretty easy, and I'm going to space these out really nicely. 1, 2, 3, 4. Recognize you can't have half a wheel, therefore we are discrete. Okay, so my bicycle, I have two wheels. So my bike, I go up and I go down, and I can shade it in, sure. My car, I have 4 wheels. So my car, I'm going to go right up and down. And recognize I'm making my bars roughly the same width. There's no point in making something a bigger width and a skinnier width. Okay, they should be roughly the same width. My motorcycle, I'm at 2. Okay. My tricycle, I'm at 3. Okay. And then my unicycle, I'm at 1. And there you go. So we plotted it. And again, why did we not use a line graph? Because it's way easier to visually see discrete data using histograms usually. Okay. Of course, sometimes you might plot it using points, which is totally fine and sometimes useful, but you would not connect these things. We wouldn't weirdly connect these points together because that makes no sense. There's nothing in between. These are unrelated. Okay, and again, the biggest important thing to understand is that these, you can't have 1.5 wheels. You either have 1, you have 2, you have 3, or you have 4. Okay, so at this point, I would now go check my understanding of 5.1. Okay, if you have any questions, please come in. Remember, every graph, every table, and every arrow diagram should always have a title, should always have your titles for whatever sets you are talking about. Okay, so in this case, we didn't really need them because it's just explained in the title, but these we definitely do. Okay, and then you also always need your units of the things you're talking about, so centimeters and years. So go check out AFL 5.1 and see how you do.